In this example, we are just going to work with algebraic techniques in order to do the kind of analysis that would be expected for a quadratic function in an application setting. So here we have a person standing close to the edge on the top of a 160-foot building, throws a baseball vertically upward. So you can assume that the baseball from the edge of the building is being thrown straight up and then coming straight back down. We're ignoring things like the effect of wind resistance, the effect of the person not being able to throw the ball perfectly vertically upwards. We're just going to assume that the ball is traveling vertically up and then coming right back down in the same path that it took going up. The quadratic function s of t equals negative 16t squared plus 64t plus 160 models the ball's height above the ground, s of t in feet, t seconds after it was thrown. So s as a function name is simply a representation for the height of the ball. And t is a representation for the time the ball has actually been in the air. In our first part, after how many seconds does the ball reach its maximum height, you might remember from our last example, asking us for the maximum height is code word for asking for the vertex. In this situation, though, we have a little bit of a different problem. We also want to determine how high the ball is at that time. So let's start by figuring out the number of seconds, then we'll transition to how high the ball is. So remembering our formula for the vertex, x is equal to negative b over 2a. For this quadratic function, we have the opposite of b, which is 64, over 2 times a, which is negative 16. And this simplifies to 2. So we can assume when x is equal to 2 seconds, that's when the ball reaches its maximum height. But we are not done yet. We now have to evaluate this function at 2, so s of 2, so we can determine the actual height of the ball after that 2-second period. Simply substituting that value of x in to the original equation will give me that location. You can check my arithmetic on this, but we should end up with 224 feet as the maximum height of the ball. So while the ball started 160 feet off of the ground, the ball was only able to travel another 84 feet in the upwards direction before gravity forced the ball back downwards, and it made that path in only 2 seconds. It was able to reach that maximum point in 2 seconds. In our next part, we're going to consider a slightly different issue. How many seconds does it take for the ball to hit the ground? Now, this is assuming that the ball could actually hit the ground. If you're standing on the edge of a 160-foot building and you throw a ball straight upwards and the ball comes straight back downwards, you would think that the ball would land right where you were standing, meaning it would hit the building. We're going to assume that the ball could actually travel all the way to the ground. If it couldn't, then this is a moot question, and you would say there's no time where it can hit the ground. So we're going to assume that we're almost like going to throw the ball and then get the building out of the way, so that the ball could then travel all the way down to that lowest point. So what is that lowest point? Well, I think it's fairly straightforward to say that that lowest point would be the ball having a height of 0. So we allow our function to equal 0. We divide everything by negative 16. Because it's equal to 0, I'm allowed to do that, and I try to clean this up. These two equations will have the same solutions, because we divided by a constant on both sides. This expression, or excuse me, that equation cannot be factored. We cannot use the square root method. So again, we appeal to the quadratic formula to find us our solutions. Opposite of b would be 4, plus or minus the square root of b squared minus 4 AC all over 2 times A. Now you can check all of my arithmetic on this, but for the sake of time and simplicity, we're going to say that this is going to be 4 plus or minus 7.48 over 2. That's what comes out of that radical. It's the square root of 56. Now it should be pretty obvious that there's a solution we're not going to need or want. If I do 4 minus 7.48 divided by 2, I would get negative 1.74. I'm going to discount that solution, ignore that solution, because it's negative. The ball is not traveling back in time. I'm only interested in the positive solution, which would be 4 plus 7.48 divided by 2, which is 5.74. So it's going to take 5.74 seconds for the ball to reach the ground. Now, here's an interesting thing to note, though, however. You might remember from part A that our vertex was at x is equal to 2. If you consider these two roots versus the number 2, you'll notice that they are each 3.74 units away from that vertex. There's our symmetry in action. If you know what the vertex is, you know then that the two x-intercepts have to be the same distance from that vertex on both sides. If you got something that it wasn't, then you would know that something was wrong. You would know that there might have been an evaluation in there somewhere wrong, or you might have ended up adding something wrong in here, or whatever it might be, but you know that you're going to be the same number of units away from the vertex in the higher direction, 5.74, and the lower direction, negative 1.74. We end with our easiest part. What is S of 0? Well, S of 0, similar to what we did with 2, is simply substituting 0 into the function, and I get that S of 0 is equal to 160. Those two terms are both 0. What does that mean in the context of the problem? Well, if you recall, we threw the ball from a height of 160 feet and threw the ball vertically upward. It was going to go up before it came back down, which means the ball is going to follow a path like this, and then it's going to come right back down on top of itself. So it's going to go up, and then it's going to come right back down on top of itself. So we should be able to recognize the role that 160 played in both the creation of the function and its job sitting here as the y-intercept. Would all of this work for this example have been easier if we had a graph to look at? Sure, we could have just pulled up a graph and identified approximations for the intercepts really quick. We could have found this point very quickly. We could have located the vertex very quickly. Every graphing technology that's worth something has those built-in functions, but that doesn't mean that we don't want to review or be aware of the algebraic techniques. So the algebraic techniques allow us to do this when we don't have a graph and we don't have that picture to rely on.